Our topic is Hero's engine, and we are going to tell its history, the phase transition of H2O and effects on pressure, the effects of hose size and force generated, the dynamic of the engine, and finally its application. Hero Alexandrinus, more often referred as Hero of Alexandria, was a Greek who lived in the 1st century in Alexandria, now part of Egypt. Little is known about Heron's life, but it's known that he was a mathematician and an engineer. Heron is considered to be the first inventor of the steam engine, a steam-powered device that was called yellow pile and also known as Hero's engine. The name yellow pile comes from the Greek word Elos, who was the Greek god of the winds, and the Latin word pila, which means ball. So what's a Hero's engine? As it can be seen on the following picture, water added to a boiler is heated with fire. The steam formed in the boiler moved to the sphere through a pair of pipes, which also served as the axis. The steam leaves the sphere through nozzles that are opposite to each other, generating a combined thrust, resulting in a torque and making the sphere to spin around its axis. The Hero's engine was forgotten and never used properly until the 16th century, when the steam engine was reinvented, but it was basically the same device as Hero. We built a simplified version of the Hero's engine. We used one pop can, line, finishing nail, 4 candles, a glass of wine deck as a support, a lighter, and water. First, we made a hole on the can with the nail and emptied it. Next, we made a hole on the opposite side of the first one, and on the both holes, we inserted the nail halfway through and bent it to the right side. Next, we bent the can tab and inserted about 5 milliliters of water. Finally, we held our engine on the support with the line and lit the candles. After 3 minutes and 30 seconds, the water started to evaporate and the can started to spin to the right side as expected, accelerating to an average of 7.5 rotations per minute.
Hello, I'm going to be talking about the phase transition of H2O and the effects on pressure for Hero's engine. We have a first couple of assumptions to make, and we're also sticking with the KISS principle because this is complicated and we have time limits. So first we're assuming that we have 1 milliliter of water equals 1 gram of H2O at standard temperature and pressure. And we're also assuming that we only have 2 grams of H2O in our can. First we need to calculate the amount of energy that it takes to bring water from room temperature up to the boiling temperature, and the amount of energy it takes to evaporate all of the water. So to calculate the energy needed to bring the water up to the boiling temperature, we first assume the room temperature was 293, the boiling Kelvin. The boiling temperature is 373 Kelvin, and our heat capacity for water at 1 atm is 4.2 kilojoules per kilogram per Kelvin. I derived our equation, which is the heat capacity times our mass times our change in temperature. I plugged in our numbers here, and we ended up having a result of 0.672 kilojoules to bring our water from room temperature to boiling temperature. Over here we have a graph of entropy times temperature. You can see how the water goes up here nice and smooth, which we just calculated the amount of energy. Now we have this discontinuity, and then we have steam. This difference, the energy it takes to overcome this is called latent heat, and this is the next energy that we need to calculate to boil off all of the water. So the latent heat of water is 2.26 megajoules per kilogram times the mass, and we end up having 4.52 kilojoules to boil all of the water. Now adding the two energies together, we get the total energy to boil, and we have 5.192 kilojoules. Now to keep this simple, I found the density of steam. I started with the volume, and then I'm basically condensing the volume down to 1 can. So here to figure out the volume of 2 grams, and the density of steam at 100 degrees at 1 atm is 0.6 kilograms per meter cubed. And working out the math here, I have a volume of 1/3 times 10 to the negative 3 meters cubed. Now I need to do another step as I'm using the ideal gas law to bring it down to our volume, and we're going to find out the pressure, because this could be used later on in the calculations. And now I wanted to find out how many moles are in 2 grams of water. And using this, you can see I calculate this down, and I end up having 0.111 moles of H2O in 2 grams of water. Now I have pressure times my number of moles, ideal gas, temperature divided by volume. So you can see this as I plug all the values in here. And then we end up having roughly 930,000 pascals, or 930,389 pascals. And changing this into ATMs, or atmosphere pressures, we're at roughly 9.1.
Now that we have some ideas to how long it takes to heat up the system and boil the water, we're going to try and get some idea as to how much force is involved. And to do that, we're going to use the concept of flux. So here is a basic model of our system. We have heat coming into the engine, and then steam coming out, and by Newton's third law, this will generate a force. So let's start off with some basic assumptions. We will assume that the ideal gas law holds, and we will assume that heat production is constant, so we can assume that steam production is constant. We will also assume that there's no flux heading into the engine, only out, and ignore any aerodynamic effects that may happen around the hole, things like choke airflow or compression of the gas around the hole. Finally, we're going to assume an equilibrium state is achieved at 100 degrees centigrade, and so all heat is transferred into the latent heat of the water to turn it into steam. We'll start by determining the amount of heat input into the system. We used 4 candles, and if we assume that each candle generates 30 watts of power, then it follows that 120 joules of heat are added into the system every second. Next, to determine the amount of steam produced, we're going to use the latent heat per kilogram as described by James previously. Then we're going to find the latent heat of 1 molecule of water by just taking the latent heat per kilogram and multiplying it by the mass of 1 molecule. The amount of heat produced then is just the heat divided by the latent heat per molecule. To determine the amount of steam leaving the system, we're going to use the idea of flux. This expression for flux comes from the ideal gas law, and we can use it to relate to the amount of particles out by taking the flux and multiplying it by the surface area of 1 hole. Then, at equilibrium, we can set the number of particles generated of steam equal to the number of particles of steam leaving the system. And we'll come up with this expression. Then, taking pressure is equal to force divided by surface area, we can rearrange that and come up with a basic expression for force. Interesting to note that the areas cancel out, and that this expression is not dependent on the surface area of the hole. Then, we can very easily go and look up the mass of 1 molecule of water, which is 2.99 times 10 to the negative 26 kilograms, and therefore find the latent heat for 1 molecule of water, which comes out to 6.79 times 10 to the negative 20 joules, and come up with a basic expression for force, which is 5.50 times 10 to the negative 2 newtons. Now, this is a very rough estimate because the model that we're using is very crude. So to go into some more depth with a more dynamics analysis, here's Kevin.
So let's get into the dynamics of Hero's engine. First, there are some assumptions that we have to make. The rate loss of evaporation is going to be equal to the escape rate of the steam coming out through the 2 holes. The force exerted on the system is going to be constant at all times, and the system is going to be frictionless, and there's going to be perfect rotation. Let's start by finding the rate of evaporation, which is given by equation 1, where Q is the heat supplied, L the latent heat, and Gs the rate of evaporation. So let's begin by finding the heat supply. 1 candle is approximately 30 watts. We use 4 in our experiment, which gives us a total value of 120 watts. We convert it to proper units, and we get the value of Q. We sub it all into the equation 1 here, and we get Gs is equals to 52.9 times 10 to the negative 6 kilograms per second. Now let's find the time to evaporate a certain mass, which is given by equation 2, where ml is mass loss, T is time in seconds. Let's assume we have ml is equals to 2 grams. We sub all that in, we get T is equal to 37.81 seconds. So let's find the total mass of the system, which is going to be the mass of the can plus the mass of the water, which gives us a total value of this. Now, because mass is changing over time, we're going to find that mass as a function of time is going to be the total mass of the system minus the rate of evaporation times the time, which gives us this equation 3 over here. Now we're going to find F, the force, by using equation 4, which relates the sum of the moments about the center of the cylinder times the mass moment of inertia times alpha. where the mass moment of inertia of a hollow cylinder is given by equation 5. And we'll be using equation 6 later on to relate the experimental angular velocity to the angular acceleration. So let's look now here at figure 1, where this is the cylinder and this is the center of mass, C. R is the radius of the cylinder, and F is coming tangential to the cylinder. Now the mass moment of inertia times alpha is moving counterclockwise here, which means it's positive. And omega is also moving counterclockwise, which means it's also positive. So now let's apply what we have from here and plug it into equation 4 that we had earlier, which gives us this values right here. Now we're going to isolate for alpha, and we're going to get that alpha is equals to this value right here. Now we're going to use the mass equation that we had earlier, and we're going to sub it into our equation. And so we're going to get this relationship right here. Now, using the omega and alpha relation, so we're going to get this equation right here, and we're going to integrate with respect to time to find an equation of omega equals to this. So by the previous equation, we find that the force is going to be a total of 2.06 times 10 to the negative 6 newtons. Now let's find the kinetic energy by using this equation right here. We plug in all the values and we get a total kinetic energy of this. Now let's find the energy input by first finding the amount of time that it will take to get water to reach 100 degrees Celsius by using this equation right here. We multiply the total time times the heat supplied and we get this equation. So now we find the efficiency of E out over E times 100%, and we get a total value of 5 times 10 to the negative 4%, which means that this is not efficient at all.
So, how does Hero's engine contribute to modern world? The truth is that the engine itself was not useful by the time it was invented. However, the concept of this invention, including the application of the properties of steam and Newton's third law, has been put to practical use later. For example, the steam engines, signal wheels, and Catherine wheels. A steam engine is a heat engine that produces mechanical work with steam. From the aspect of thermodynamics, we use the Rankine cycle to analyze the process. In this cycle, water is heated into steam and reaches high pressure in the boiler from step 3 in the picture. Then, the high-pressure steam expands through pistons or turbines to do mechanical work. Finally, the reduced pressure steam is condensed, turned back into water, and pumped back into the boiler to start a new cycle. A signal wheel is a water turbine using the principle of Hero's engine. In a signal wheel, water is delivered into the top of a vertical cylinder from point A in the picture. At the bottom of the cylinder, there are designed bent pipes with nozzles on their ends. Water comes out from these nozzles and causes rotations. The torque can be then transferred into some other power device to do work. Today, this principle is mainly used in the irrigation sprinklers, where water is ejected through specific nozzle to cause rotations, which allows the system to sprinkle water around. A Catherine wheel is a kind of firework named after St. Catherine of Alexandria. It consists of a power-filled spiral tube or an angle rocket mounted with a pin through its center. By Newton's third law, that for every action there is an equal and opposite reaction. So when the fire powder is ignited, the hot gas is expelled, and making the system rotates quickly to produce a display of sparks and color flame. A simple toy like Hero's engine can lead to great inventions later. What is your thought about the properties of steam and Newton's third law? Can you think of any other applications?
Đi ra một con